In this last video, I wanted to show you a couple of examples, revisiting examples that we've learned in LambdaF that motivated us to change the whole language so that we could finally be able to represent defines accurately with respect to racket. So let's look at this example. We want to first define B and then define A and call B after A is defined. And this should be fine, and it failed in LambdaF because in LambdaF there was no propagation of side effects, and therefore this would be an invalid program. But in LambdaD, I want to convince you that it actually works, and let's see how. So in the first step, what we see is we have on the left-hand side the inputs of our function, and then we're going to see the outputs. And on the bottom, I'm going to show you how to interpret the rules. So you should be looking at the rules and contrasting them with what I show you on the bottom. Basically, on the bottom, you can it's a visualization of how the various pieces should work. So it's kind of like if you imagine a debugger would step through your code. This should be the inputs and outputs of every function call. So let's see. If we evaluate the first define, right, this define on the top, which is the input term, and let's say my environment that I'm executing is 0, and everything above the line is the heap. So my heap is initialized with just an environment E0 that is pointing to an empty environment. So let's see how evaluating this define affects the heap, which is defined here, and the return value, which is void. So we have two outputs, 3 inputs, and 2 outputs, right? The outputs are the new heap, which I'm representing everything up to the last line, and the last line is the value that I'm returning. The reason I'm not putting dash 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 is because it becomes very big. So it's kind of, this is better, otherwise it won't fit in the slides. So let's try to interpret what's going on. So what we're saying is if we execute a define, the output should be, the value should be void, and my new environment should have just one binding, which is B, right? Because I'm defining B. And what is B? B is the evaluation of the lambda. Evaluating the lambda should return a closure, right? So if it returns a closure, the closure should capture the reference E0, which is the enclosing environment. Perfect. So that makes sense intuitively, right? So let's see how that affects in terms of rules. So let's instantiate them. So in my rule, what I have is a define, and then the input environment is E0 because of this. Then what I have to do, I have to execute 2 things. The first thing is the recursive evaluation of the lambda. And I see it here. And what I see is that if I recursively evaluate the lambda with E0, I should get this closure. Right? It's not saying anything about the heap because it's implicit, the heap. Then I should take the heap that I got from this evaluation, and what should I do with it? I should perform a put. So I should perform a put on E0, and then I need to put B and the closure that has E1 and the lambda, right? So that's why here you see that the output heap, which is implicit in the rules, becomes explicit here, has B and the closure, which is this part. So this closure represents this, B represents this, so the output of this operation should be this, and the value void corresponds to this void. So now let's evaluate the second line, which is A to 20. Evaluating A to 20 is easier, it's very similar. We define, we recursively evaluate 20, which returns 20, so it does not affect the heap, but you have to return, the return value of this heap should go here. What do I do here? I assign A to 20, right? A to 20. And here in the output, I see that the new thing is that A is assigned to 20. return value is still void. So finally, let's evaluate b1. So I'm doing a function call. In your interpreter, you cannot assume anything about b. It could be anything. In this case, it's a variable, but it's just for the sake of having a small example. Okay, so what happens when we do that? We have to evaluate b. B is a variable. How do we evaluate b? We evaluate b by looking up in the input heap, right? In E0, what is the value of b? In E0, the b is this closure, which matches exactly what is here. E0, and then lambda y dot a, right? This part is this part. So that's the evaluation of the function. And then I need to evaluate the argument. So I'm going to take the resulting heap from here, and I'm going to pass it here to the second recursive call. Evaluating a number returns itself. So that's fine. Pass the return heap from here to here. Now what we do, we have to push, right? We have to perform a push operation. Push operation takes two parameters, actually three. The first one is the heap. Second one is the environment E0, which is given from here, right? And then we are going to extend it from here. And then we're going to extend it with y equals to 1. So notice what happens in our output heap. Our heap now has a new entry, which is E1. We allocated something in the same heap. So E1 has everything that is in E0, so I'm representing it in this notation, plus y assigned to 1. So the output of pushing is visible here. E0, so we're extending E0 with y dot 1. And this output is actually what you will see in the test cases. Okay, and finally the value is 20. Why? Because I need to evaluate A in my environment E1. So let's see what happens. When we evaluate A is a variable, right? So because it is a variable, we have to look up A in E1, right? So if I do E1, I need to look up A. A is not defined here, but it is defined in E0, which means I need to somehow navigate E0, to the extension, right? Because here I'm saying all the bindings that are in E0 plus y. So that means if A is not in E1, we have to look it up in E0 because I'm referencing it here. And now what I see is that A is there, so I return 20. And therefore the whole thing should return 20. Okay, so now let's look at another example, which is a simpler example. It's just I have f of x, right? I'm defining a function that inside has another function that returns x, so the outermost x. How do we represent that? Let's see. Good. So if we have an input that, the output should be, we should have a new function, right, that has a closure E0 and returns this. This should be fine, right? Let's see how that returns. So when we evaluate f, that is two lambdas, one nested inside the other, right? The outermost and the innermost. And if we pass E0, what we're doing is we're going to evaluate the outer lambda, and that should return a closure with E0. So we're mutating the environment E0 because this is a define, right? So now we just have that represented. Okay. So this is exactly this, nothing too surprising. So now what we're going to do is I want to call f and pass number 10. So I have to look up variable v in environment E0, and that's going to get me this closure. And then I'm going to instantiate this closure with the number 10. So I'm going to replace this x by 10. So whenever we call a function, what we do is we create a new closure. sorry, when we create a new environment, right? Let's see that happening, because we have to do this push. So let's see, I'm calling f with 10, function f with argument 10. So the first thing we're going to do is just looking it up, right? So we're going to look up this closure on f, right? Because it's available in E0, E of 0 of f is just the closure itself. That's fine, nothing too surprising. And then I'm going to evaluate 10, that returns 10, that's also basic. So now let's see what are we doing here in the second command. In this second command, we're doing a push, right? So that means we're creating a new environment, let's call it E1. And E1 is going to extend E0 with the binding x10. And note that x10 is the outermost value. It's painted in blue. Okay. So x10, x is assigned to 10. Perfect. So what do we do now? Now we have a new heap where I have E1, where I've extended E0, and I added the binding 10 to 10, x to 10. Okay. And now what do I have? I'm going to evaluate the body, which is the innermost thing. And I'm going to evaluate that, and I'm going to evaluate it with which closure? Not the closure that is outside, but the closure that we just created, right? Which means whenever we create a closure, it's going to capture the environment that was defined inside of it. So in this case, E1. See if that makes sense. Let me write it down. So the original example was this. Oops. Right. Actually, do this. Okay, so we're defining f, right? And this is E0, the outermost. And let's say that this inside is E1, right? And now I want to actually define G to be all of this, right? Okay, what this example is trying to show you is that whenever I call f, right, and I pass a parameter, this is like the factory function that we defined a long time ago. That returns a new lambda, right? But that lambda, is going to return, in this case, if I call G of 20, I should get back 10, right? Because it's the value I initialize it with. So I should get 10. And if I define H and I call F with 20, let me use another number so it's not confusing, 30, and I call H with 40, I still get 30, right? Because it's the value that I created the variable with. So what this example is trying to show you is that you might be wondering, why am I creating in my shared memory, whenever I call a function, why do I create a new heap and I keep it around? Why don't I just remove it, right? Because in this previous example, I call this function b of 1, and I just had this environment, but it's useless, this environment, right? You may be wondering, so why is this environment here? So an example of why it needs to be here is this example that I was just showing you. If you lose the environment E1, so whenever I I call a function, the idea is that I'm going to create a new environment E1. So I'm going to call it E1.1. It's going to be E1 where x equals 10, and this is going to be E1 where x equals 30. So you're going to have, whenever you call a function, you're going to create a new closure, and this closure is capturing in a new environment, right? The environment that contains any variable that I define, right? If I define z equals 10, E1 should have 10, but not E0, right? Because this is inside. There's another scope here. So what we're saying is, whenever we call a function, we need to create a new clean environment, right? But we cannot lose this environment. Otherwise, whenever you would call this, the environment would go away. So you need to keep it around so that, let's see, so that whenever I call the function, I don't lose the environment, because the closure, because there might be some closure still referring to this E1, right? So in this case, this lambda is referring to E1, where z is 10 and x equals z equals 10. So the environment here, x equals 10 and z equals 10, because I've defined z to be 10, right? And here, but here, whenever I call g, I have to be able to access this instance of E1, right? So whenever I call function f, I get a new instance of E that is bound to whatever parameters I gave it. And that's basically why you have to keep these environments around. So your shared memory is ever growing, which is kind of a very naive implementation. And if you want to optimize it, you should implement some notion of garbage collection, which we'll cover in a later lesson. But if you follow just the rules, it's a very simple example and another variation of why you would do things. So that's basically it. This example 3 was mostly to remind you that you cannot, why you actually need to have a shared memory that is ever growing. Whenever you call a function, you're extending your memory. You call another function, you call the same function 3 times, your heap is going to create 3 new instances, because it needs, it doesn't know at this point, we don't know how to garbage collect ones that are useless and or ones that are actually being referred by some closure. Because here the problem is that if you create any lambda inside a function call, that closure is going to be the closure that was, the environment that was created just to call your function might be referenced by some closure. That's the main idea here.